day 16 of 60 in our DSA in Rust challenge. And today we're going to break your brain in the best way. Binary search has almost nothing to do with sorted arrays. Here's the wall most developers hit. Leak code says minimize the maximum load or find the kth smallest in a grid you never build. And you freeze because you know binary search means find x in an array. By the end of 5 minutes, you'll see binary search for what it really is, a reasoning tool for any monotonic predicate, and Rust's ownership rules will make that predicate impossible to misread. So what is a monotonic predicate? Picture a row of answers from smallest to largest. For every candidate, you ask one yes or no question. Is this answer feasible? If the answer flips from false to false to false, then true and stays true forever, that boundary is monotonic. That single flip point is what we're hunting. We are no longer searching array indices. We're searching the range of possible answers. Take a capacity problem. N tasks with integer weights, k workers. Find the minimum max load any worker carries. The smallest possible answer is the heaviest single task. The largest is the sum of all tasks. Somewhere in that range is the flip from can't distribute to can distribute. Notice we never sort anything. The predicate is the whole algorithm, and that reframing from indices to answers is the entire lesson today. Let's write the generic engine in Rust. Fn bisect f, fn I64, bool, mut low, I64 mut high, I64, pred, f, I64. We work a half-open interval, low inclusive, high exclusive. While low is less than high, compute let mid equals low plus high, low, /2. That subtraction avoids overflow. If pred, mid, is true, we found a feasible answer, so high equals mid. Otherwise, low equals mid plus 1. When the loop ends, low is the smallest value where the predicate holds. Here's the Rust magic. Pred is a generic fn, so the caller passes a closure that borrows problem data. The closure captures tasks and workers by shared reference. No clone, no fight with the borrow checker. And because the borrow is immutable, the compiler guarantees the predicate cannot accidentally mutate your search state mid-run. That's not a constraint. That's correctness for free. Now wire it to the worker's problem. We write fn can_distribute, tasks, u32, workers, u32, capacity, u32, bool. Greedy, walk the tasks, keep a running load, and whenever adding the next task exceeds capacity, start a new worker and reset. Count workers used. Return true if we stayed within k. The slice comes in as u32, an immutable borrow, naturally. Then in main we call bisect like this. Bisect, max_task, total plus 1, cap can_distribute, tasks, workers, cap as u32. Watch how the closure reaches out and borrows tasks and workers from the surrounding scope. Run it on tasks, 10, 20, 30, 40. With 3 workers, and you get 60. Worker 1 takes 10 and 20, worker 2 takes 30, worker 3 takes 40. The predicate took the borrow, the engine never touched your data, and the answer is right there on the page. This same engine solves the kth smallest in a multiplication table. The predicate is count_lt, m, n, mid. How many products are less than or equal to mid? And it's pure arithmetic, 0 allocation. You never materialize the m by n grid into a vec. Compare that to the naive approach that builds the whole grid and sorts it. You've traded megabytes of allocation for a handful of integer divisions, and the code is shorter. So here's your one-sentence rule for spotting these in interviews. If the problem says minimize the maximum, maximize the minimum, or find the kth smallest in a structure you'd rather not build, reach for binary search on answers. 3 to try tonight. Minimum capacity to ship packages, split array largest sum, and kth smallest in a sorted matrix. Day 16 done. Stop searching indices, start searching answers, and let Rust borrow checker prove your predicate stays pure. Subscribe for day 17.